Next slide. Before I talk about biomarkers, let's look at this idea of the habitable zone. There's a range of distances within which the surface temperature could be nice enough for liquid water to exist on the surface. Note the water bias and the surface life bias here. The type of life we're going to be able to detect from tens to thousands of light years away is life on the surface of the planet. And even with the water limitation, we're expecting to find a lot of suitable planets. The habitable zone of a hotter main sequence star will be farther out and wider because of the hotter star's greater luminosity. Using the same line of reasoning, the habitable zone of a cooler main sequence star will be closer to the star and narrower. Unfortunately, the hot luminous stars with big, wide, habitable zones live very short lives. If life on Earth is any sort of guide for how long it takes intelligence to arise, then we're going to want to focus our attention on stars that live for at least 3.5 to 4 billion years. On the other hand, stars smaller and cooler than the Sun are very common, with the so-called M-dwarf stars making up 75% of the stars in the galaxy. But they have very small, thin habitable zones. Exoplanets in that close to their star will probably become tidally locked like the Moon is to the Earth, so that one side always faces the star and the far side is in perpetual night. One side hot and the other side so cold that the atmosphere could freeze out. Newer models of atmospheric physics seem to show that a tidally locked planet could still have locations with comfortable temperatures if there's a thick enough atmosphere to circulate heat from the day side to the night side. Those comfortable places are near the day-night boundary. If those computer models are correct, then we're in luck, because the Kepler mission found that at least 50% of the very common M stars have a planet between 0.5 to 1.4 Earth diameters orbiting within their habitable zone. In fact, the closest star to us, Proxima Centauri, is a M-type star, and it has an exoplanet with a minimum mass of about 1.3 Earth masses orbiting in the habitable zone. Wow! This graph shows the exoplanet size versus the exoplanet surface temperature for the exoplanets found so far. The ones in the box are the particularly interesting ones that are between 70% to twice the Earth in diameter in an optimistic habitable zone of their star. Select the image to bring up the current plot. Is it possible for habitable planets to exist in binary star systems where two stars are orbiting each other? We used to think stable orbits in such systems were not possible, and that was worrisome because the majority of stars are in a binary or triple star system. Solitary stars like the Sun are in the minority. Exoplanet searches, especially the Kepler mission, have shown us that habitable zone planets in binary systems are possible. You can have stable habitable zone exoplanets if the binary stars are really close to each other and the exoplanet orbits them both, like Tatooine of Star Wars. Or if the two stars are far enough apart and the exoplanet orbits one of the stars. Any life forms will need to use some of the elements heavier than helium, especially carbon, nitrogen, and oxygen, and probably also phosphorus, sulfur, chromium, iron, and nickel for biochemical reactions. This means that the gas cloud which forms the star and its planets will have to be enriched with these heavy elements, called metals by astronomers as a catch-all term, from previous generations of stars. If the star has a metal-rich spectrum, then any planets forming around it will be enriched as well. While it may be possible for life to exist on a planet or moon below its surface, we will not be able to detect its presence from a great distance away. For example, if it is in a star system beyond our solar system. In our fastest rocket-propelled spacecraft, it would take us over 70,000 years to travel to the next star system, Alpha Centauri. The type of inhabited planet we will be able to detect outside of our solar system is life that has changed the chemistry of the planet's atmosphere, which means the life will have to be on the surface. By analyzing the spectrum of the planet's atmosphere, we may be able to detect biomarkers, spectral signatures of certain compounds in certain proportions that could not be produced by non-biological processes. Biomarkers are also called biosignatures. Spectral lines from water would say that a planet has a vital ingredient for life, but it does not mean that life is present. If oxygen, particularly ozone, a molecule of 3 oxygen atoms, is found in the atmosphere, then it would be very likely that life is indeed on the planet. Regular molecular oxygen with 2 oxygen atoms does not produce absorption lines in the preferred infrared band that will be used by infrared telescopes hunting for inhabited exoplanets, but ozone does. Ozone, existing along with nitrous oxide and methane in particular ratios with carbon dioxide and water, all of which produce absorption lines in the infrared, would be strong evidence for an inhabited world. The ratios would need to be off-kilter, not in chemical equilibrium, that is, not in ratios made by normal geological processes. For such worlds found with these biomarkers, further modeling of what strange non-biological water cycles and volcanic activity very different from that found on Earth could produce the large amount of ozone would need to be done before we could definitely conclude that the exoplanet had life on it. It is a very big step to go from finding a planet that could support life to saying that the planet does support life. Next slide. This slide I show in conjunction with showing the film Life Beyond Earth by Timothy Ferris. The Drake equation is a way to estimate the number of communicating advanced civilizations, big N, inhabiting the galaxy. It is named after Frank Drake, who first summarized the things we need to know to answer the question, how many of them are out there? The equation breaks this big, unknown, complex question into several smaller, hopefully manageable parts. Once you know how to deal with each of the pieces, you can put them together to come up with a decent guess. R star is the star formation rate, which is now about 2 stars per year in the galaxy, but was higher in the past. F sub p is the fraction of stars with planets. The census of stars by the Kepler mission has shown that at least 70% of ordinary stars, including those hotter than the Sun, and the great majority cooler than the Sun, have a planet of some size orbiting them. The percentage will only increase as the Kepler and TESS teams process their data. N sub e is the average number of Earth-like planets per suitable star system. Earth-like here means a terrestrial planet with a solid surface and liquid medium on top to get the chemical elements together for biochemical reactions. The planet has strong enough gravity to hold on to an atmosphere. F sub L is the average fraction of Earth-like planets with life. Extrasolar life will probably be carbon-based because carbon can bond in so many different ways, and even with itself. Therefore, carbon can make the large and complex molecules needed for any sort of biological processes. F sub I is the average fraction of life-bearing planets evolving at least one intelligent species. Is intelligence necessary for survival? Will life on a planet naturally develop towards more complexity and intelligence? Complex multicellular plant and animal life is more fragile than simple microbial life. So while new research seems to increase the F sub L term, the F sub I term might be smaller than initially thought. If the rise of intelligence is accidental, then the F sub I term will be nearly zero. If intelligence is an emergent property of any biological system, then intelligence would be an expected result of complex life, boosting the F sub I term. An emergent property is a property that arises when a simple system with a sufficient number of interacting parts spontaneously becomes more complex. The property cannot be seen in individual members of a system, but can be seen only in large assemblages of them, complex behaviors of a collective that are more than just the sum of the individual members. F sub c is the average fraction of intelligent-bearing planets capable of interstellar communication. The intelligent life we will be able to talk to will have to use some sort of symbolic language. Will intelligent life want to communicate to beings of a different species? Capital L is the average lifetime, in years, that a civilization remains technologically active. How long will the civilization use radio communication? Will they be around long enough to send messages and get a reply? Even if we manage to take better care of the Earth and each other, our technology is changing, so we may not use radio communication. Because of the huge interstellar distances in the galaxy, the big L term is the most significant constraint on communicating with an extraterrestrial. We are more certain about the first set of terms, but get increasingly uncertain as we go to the right. The picture also shows that the various terms act like a set of filters. So even with a lot of stars, you could end up with just a few ET civilizations for us to talk to. Once you have an estimate of the number of communicating civilizations in the galaxy, you can estimate the average distance between civilizations. Clearly, the larger the capital N, the shorter is the separation distance. Next slide. Since we're stuck in our solar system, we're hoping that the ET civilization will be able to make their presence known from radio signals leaking out or from nanosecond bursts of optical lasers. Most searches for extraterrestrial intelligence focus on the radio band, especially around 1400 megahertz, for 4 reasons. 1. The galaxy has the lowest background interference at this frequency range. 2. It is the emission frequency from hydrogen which any intelligent civilization would know about and would build devices to detect and transmit those frequencies of light. 3. It is not blocked by dust, so transmissions would go a very long distance. And 4. It is a low energy form of light, which means it should be cheap to produce. This graph shows the amount of static or radio noise versus frequency produced by various things. The so-called water hole is where the background interference, the noise, is smallest, not only for us, but for anyone else in the galaxy. Other SETI searches are looking for very brief, nanosecond optical, visible light flashes because visible light can travel great distances out of the galactic plane, and a tightly focused beam of light, like a laser, can be made many times brighter than a star for very brief pulses just a nanosecond long. If the beam of light is pointed our way, we could see it over the glare of the star the extraterrestrial's orbit. Also, the higher frequencies of visible light than radio means that a larger amount of information could be transmitted in a given amount of time than with radio. Perhaps the extraterrestrials would use radio signals to make their presence known and use lasers to beam information to us once we have started looking their direction. The Life Beyond Earth film talks about UFOs as space aliens, and I wrote a paper about this topic that is posted on the Astronomy Notes website, and there's a link to it in the class Canvas. UFO research is actually pseudoscience. With pseudoscience, the standards of argument and what is allowable as evidence are much more relaxed than what you find in true science. Go back to that article, 7 Signs of Bogus Science, I asked you to read in the first week of the semester. In my UFO paper, I used passages from Carl Sagan's book, The Demon-Haunted World. Sagan noted that perhaps the sharpest distinction between science and pseudoscience is that science has a far keener appreciation of human imperfections and fallibility than does pseudoscience. This is why conclusions based solely, or even mostly on eyewitness testimony are not acceptable in science, however harsh that may seem to the layman. In my UFO paper, I include a link to the Invisible Gorilla website that gives powerful examples of our perceptions, intuitions, and even the reasoning about our intuition, leading even the best of observers astray. That is why we have the peer review process of science. Valid scientific evidence is objective, instrumental observations of the same phenomenon that has been verified by two or more independent research teams and is therefore repeatable. It is not based on eyewitnesses because of the well-demonstrated unreliability of people's memory. The link is to the Invisible Gorilla website. Carl Sagan noted that extraordinary claims require extraordinary evidence. There is a lot of junk science on the internet, and Google or Bing do not have any quality filters in their search results. I recommend that you stick with the claims that have undergone repeated critical peer review.